Well, I'm going to show you how to work what we call an equilibrium problem when you're studying forces. It's a real common situation, and they sound something like this. If you have a certain number of forces acting on an object, what is the one additional force that you could use in order to put the object in equilibrium? And equilibrium just means it's not going to be changing its motion. So oftentimes it's to keep something from moving. For example, civil engineers need to make sure that their bridges and roads are pretty much in equilibrium, just very tiny movements, if any. Architects need to plan for that. And so I'm going to show you just a simple model of one where we've got three forces acting on an object that we know about, and we're looking for the fourth force that's going to put it in equilibrium. So let me just draw a little picture of what I had in mind. That's our object, and the three forces that we might know, I'm not going to draw these to scale. Maybe this is F1. We'll call it 10 newtons downward, and F2, we'll send that up here. We'll call that 50 newtons, and we'll say that that's pointed at 20 degrees above the horizontal. And then we'll put maybe 30 newtons out this way towards the left. Refer to that as F3. And then your job would be to find the fourth force that it would take to keep that thing in equilibrium. So it's hard to tell looking at it right now in what direction that's going to point. So I'm not going to try to draw it. I'm just going to show you how we calculate it. And the key mathematical relationship when you're in equilibrium is that all of your forces add up to be zero. Another way to say that is all your up forces are balanced by a down force, and all your left forces are balanced by a right force. So what I'm going to do is I'm going to start for the horizontal motion. I'm just going to write a mathematical statement to that effect. And here's how we write it kind of in a fancy math form. We use the symbol sigma. That means the sum. So the sum of all the forces in the x direction, those are x components, has to equal 0. And so if we write down what those are, well, F1 has no component in the x direction, so I'll just put a 0 in for that. You typically wouldn't need to do that. F2, remember I called this F2, that 50 newtons is not pointed horizontally, but part of it is. So F2 would have a component in the horizontal direction of 50 newtons times the cosine of 20 degrees. And then F3 is pointed leftward. I'm going to call that the negative x direction, so I'll add a negative 30 newtons. And then my unknown force, F4, whatever its x component is, that's the one that I need to add to total up to be 0. So if we do the math, and I've done the math previously for this, you'll solve for F4 in the x direction, and you'll get about 17 newtons. I'm rounding a little bit. Then we do a similar thing in the vertical direction, except we're going to sum up all the vertical components, so we'll call that the sum of all the y components, and those have to equal 0. So again, going through the three that we know, we got a downward of 10. I'm going to call downward the negative directions. And then we have an upward component of F2, so that would be 50 newtons times the sine of 20 degrees. F3 is completely horizontal, so it has no y component. And then my unknown, the y component of F4, is what I'm looking for to total up to be 0. And so that y component comes out to about 7.1 newtons. And I just realized, and you may have been doing this yourself, it'd be a good thing, I missed a negative sign on that x component, so make sure you go back there and put that in. That's going to be important when we do this last step, because I'm going to want to know not only the magnitude of this fourth force, but also what direction it points. So now I've got these two components of this force I'm looking for. Now I just need to put those components together the way you've learned to put components together. So I like to draw it first. So I have a leftward 17 and an upward of 7. Try to draw it somewhat close to scale. So I want my 17 to be over twice as long as my 7.1. And then I'll just draw it in red here. From the point where we started until where we end, that's that fourth force that I'm looking for. And now we can tell which way it points. It points mostly left and a little bit up. And we would be looking for how long that is. That's a Pythagorean theorem. And so the magnitude of F4, sounds like a tornado, is 17 squared plus 7.1 squared and then square rooted. That gives me about 18.4 newtons. And then we would calculate the angle here. We'll call that theta. I'm running out of room. I'm just going to tell you that I came up with a theta of about 22 or 23 degrees, I guess. But I can't report that as 23 degrees because look where that's pointed. That's how far above leftward it is, or the negative x direction. So I need to take 180 minus 23, and that's 157 degrees. And that would be the proper way to report that using our counterclockwise from positive x orientation. So that's a good example of how you can mix components in with an equilibrium problem. Hopefully the ones you see kind of resemble that. We'll call that it for now. Good luck.